Hello everyone. Let's welcome our next speaker in Security Dev Room. It's Gils and his talk about incrementality and deck functions.
Thank you. Welcome everyone. Thank you for attending my talk during the lunchtime or almost lunchtime. So indeed, in this talk I will talk about symmetric cryptography. And I will talk about some considerations we've had recently around the notion of incrementality. So when I say we, in this presentation, everything I'm going to say is joint work with the rest of the Ketchak team, namely Guido Bertoni, Johan Damens at Offert, Michael Peters, and Ronnie van Keer. So just a bit of background on what we do. So we are interested in permutation-based crypto. So permutation-based crypto is something, a new kind of crypto in the sense that we, instead of having a block cipher, we use a keyless permutation. The name Ketchak Kim comes from the designers, originally from the designers of Ketchak, which was selected as SHA-3 during the SHA-3 competition. We designed many stuff based on permutations. So we didn't stop at hashing. We also looked at encryption and authentication. We developed some new constructions. One instance is key Duplex, another one is Farfalle. From these you can build encryption scheme, authentication schemes, or authenticated encryption schemes. And we develop, of course, we design some specific instances. But yeah, in this talk, it's not going to be about all these new schemes. Instead, I would like to talk about what I call incrementality. So incrementality is the notion that if you have some kind of cryptographic primitive, you have some input, some output, you can, from the input, get some output, and then you can take your input and you increase, you add some more string to your input and you get another output, then you add more string, you have another output, and so on. You every time get some output on everything that you have, on constructing your inputs step by step. The key thing about incrementality is that every time you do that, you don't have to start all over again. You only pay the price for the additional string that you're adding to your input. That's what I mean with incrementality. And we're trying to look around this notion, and we think it's an ingredient that can help simplifying symmetric crypto. So that's our goal. We want to do something that is simpler in terms of description, in terms of implementation, when it comes to authenticated encryption. We recently developed something called a deck function. So a deck function is not a new construction on top of all your other constructions that I mentioned. It's more an interface, something that aims at capturing the notion of incrementality. And on top of this interface, we can build modes for authentication, encryption, and authenticated encryption. Okay, so in this presentation, I will talk first about incrementality, and for that I will take as an example the Disco protocol, and then I will talk about deck functions more specifically. So why is incrementality useful, and in the sense that it can help us simplify things? So the Disco, I will explain of course what the Disco protocol is, but to start I need to go back to the basics. And the first, let's say, incremental construction that we defined was the duplex construction. So the duplex, if you may know that the Ketchak uses the sponge construction. The duplex construction is just cryptographically equivalent to the sponge construction. The only difference is the interface. The interface allows us to have input, one input block, one input block, one input block, one input block every time. So it uses a permutation. The permutation is F here. You have some block of input, and you can get some block of output. Then you have a second block of input, permutation, block of output, and so on. And if you look at maybe this block of output, this block of output is going to depend on all the past input blocks. So we have this notion of incrementality. But as such, the duplex is not really useful. We need to have some layer on top of it to build something concrete and useful in crypto. One thing that we can do is to use the Strobe protocol. So the Strobe protocol was designed by Mike Hamburg, and it was presented at Real World Crypto 3 years ago. And so it's just a layer on top of Duplex, but it provides a really nice and simple syntax on, that you can use, for instance, to build secure channels or to hash the transcript of a protocol. And it's simple enough that it allows for a really compact implementation. So in terms of lines of code, it's fairly compact. Concretely, what can you do with the Strobe protocol? You can have some, these are the functions, you can have some associated data, that is some data that does not need to be encrypted, but you need to authenticate. You can input a secret key. Actually, you would start with inputting the secret key. You can get some output, PRF. And then there's this notion of client-server communication. You can send data in the clear, but besides sending the data, the state of Strobe will be affected by the data, so it will authenticate. When you authenticate, it will also authenticate the clear text data. Receive clear text is the equivalent, but from server to client. Send encrypted, I'm going to send some data, but in an encrypted form, and my state is going to depend on it. Receive is vice versa. I'm getting some ciphertext, and I want to get back the plain text, and I want my state to depend on it. Send MAC, I need to authenticate myself to the server. I send a message authentication code, depending on everything that was done so far. Receive MAC, I get a MAC from the server. I need to check that it fits my key and my context. And then finally, ratchet is something that ensures forward secrecy. So it erases part of the state in a way that you cannot go back in case the state gets compromised. Here is a small example of a protocol on top of Strobe. So it's a really simple protocol in the sense that we have a client and a server. The client is going to request a file. We want this request to be encrypted, so the name of the file is going to be encrypted. And we want the server to send back the file in an encrypted form. So I start by putting my secret key here. It's either a pre-shared key or a key that comes from a public key operation like Diffie-Hellman. And then I have some context X that is going to summarize on what the state depends. And I start with an empty X. So the next operation is AD. So I'm going to add to my context some associated data, in this case, the string nonce and a sequence counter I that is going to be incremented every time I use it. Then the string auth data, followed by the IP addresses of the client and the server. So when I write that X gets incremented with all these strings, it doesn't mean we have a buffer with all these strings. It means that these strings are absorbed, and the state of the cryptographic object, the duplex object underlying Strobe, somehow contains a hash of everything that is in X. Then I want to send my request, get file. File is being a file name. I just encrypt this string get file under the key K, and that's my ciphertext that I send to the server. And at the same time, I update my context with this get file string. Then I send a message authentication code that depends on the entire context. So from the entire transcript of the protocol so far. Then the server sends me back the file in ciphertext. I'm going to decrypt it and get the plain text, so the file in the clear. I update my context accordingly, and then I check the MAC. The MAC contains everything, and in particular, it contains the plain text that I just received. So I'm now sure that my file was not tampered with on the way from the server back to me. Okay, so in the end, it's fairly nice syntax. You can build many things of this form. Then, so Strobe is only about the symmetric key part. What about the public key part? There is another protocol called the Noise Protocol Framework, defined by Trevor Perrin and presented at Hello Crypto 2 years ago. It's a fairly popular protocol in the sense that it's used, for instance, in WhatsApp and WireGuard. It does two things. First, it handles the public key handshake, so it does typically elliptic curve operations to establish a common secret key, and then it also handles the secret key encryption and authentication aspects. In this diagram, so you can see what's happening inside Noise. So I'm focusing on everything. I'm not going to detail this figure. I'm just showing it to point out that it's fairly complicated when it comes to describing what happens in the symmetric part of noise. So you have different primitives, you have hash functions, key derivation functions, cipher, so authenticate encryption, and all that gets mixed in a fairly complicated way. So the idea of Disco. So Disco was presented by David Wong at Black Hat 3 years ago, and the idea is just to take noise, but replace the symmetric part of noise with something based on Strobe. And the idea is to make things simpler. And if you take the previous figure and now you look at Disco instead of noise itself, then you can see that the symmetric part is much clearer. It's just one call to Strobe every time. The entire state is maintained by Strobe itself. There is no need to have different things running in parallel somehow. You may say, okay, but maybe now the complexity is hidden behind these function calls. Well, if you look inside these functions calls, it really relies on the duplex construction, which as operations only need to XOR some strings into the state and apply the permutation when it's needed. So the kind of operations that lie behind these functions calls are really simple. And that makes the implementation of Disco really nice, really simple. Here are some figures provided by David Wong about the size of Disco written in C, C#, and Go. And you can see that Disco fits in a few thousand lines. If you compare that to OpenSSL, it's of course much smaller. I don't think these figures are really fair because OpenSSL does a lot of more things and they have many options to look at. But still, I mean, my point is that Disco is really simple. And one aspect of it is the use of the duplex object and its incrementality to allow for this simplicity. Okay, so starting from incrementality, we decided, yeah, let's take a step back and look at how can we define incrementality, how can we maybe refine this notion and try to define things on top of a new object, a new interface that we call DEC function. So what is a DEC function? I'm sorry, that's the most technical slide of the presentation. It has some notation, but basically a DEC function is a pseudo-random function that takes as input a sequence of strings. So the input is either one string, or two strings, or three strings, and it's a deterministic function, so it takes a secret key and this sequence of strings, and it's going to produce as many output bits as you wish. These output bits, they depend on secret key, they depend on the input. If you change just a single bit of your input, you get some unrelated outputs. It's deterministic, so if you know the secret key and of course you have the input, you can compute, and if you compute it twice, you get the same result. It's pseudo-random in the sense that from the point of view of an adversary who doesn't know the secret key, these output bits, they just look like unbiased random bits. An adversary cannot predict them for a new input stream. So I said it takes, it outputs as many bits as you want. Of course, you don't need an infinite number of bits. And this notation is, I'm not going to detail the notation, but it just says that I can take n bits starting from offset q. Okay, that's a DEC function, but that's not all of it. Another requirement of a DEC function is to allow for this incrementality. Maybe I forgot to mention that DEC stands for doubly extendable cryptographic key function. So doubly extendable is really the feature I'm now describing, which is the incrementality. I want to have extendable input and extendable output. By extendable input, I mean, let's say you first compute fx over some string x, and then later on you want to compute fx over y after x. But you already computed f of x, you have maybe kept some state. Then if you do that, the computation of fy after x does not cost you, because the cost only depends on the length of y, not the length of x. You don't need to start all over again. You don't need to pay for evaluating f of y after x if you already evaluated f of y. So that's incrementality on the input. On the output, it's also very simple. I mean, you can take some bits of output, and if you need more, you just pay for these extra bits. You don't need to start all over again. Okay, so that's the doubly extendable feature of a DEC function. Okay, so now assume that we have some DEC function. I'm going to, of course, describe how we can build one concretely, but assume we have one. What can we do concretely with the DEC function? First application, very simple application. I want to just to encrypt some data. So I have my DEC function. I input the secret key and I input some sequence number, a nonce, and then the output, I use it as a key stream. I XOR every bit of my plaintext with the corresponding bit of the key stream, and the result is my ciphertext. To decrypt, I just do the same. I XOR the key stream to the ciphertext. And if you XOR the same thing twice, they cancel each other, and you get back the plaintext. So encryption, stream encryption, very simple application. To do authentication, you input your message to the DEC function. The output is your authentication tag that you attach to your message. Okay, now about incrementality. So you can have this DEC function, the output is going to depend on everything that was received so far. So if you maintain a DEC function and you encrypt different messages that follow each other, then you can have something which we call a session. And by session, I mean that if you exchange some messages, let's say you exchange 3 messages, the tag on the third message, so the authentication of the third message, is not just locally authenticating this third message, but really the sequence of all the messages received so far. So maybe this last message is just a confirmation. It's just a big OK with the tag. You don't want the adversary to be able to reuse this OK in different contexts. Otherwise, the adversary could send an OK on something you don't want, maybe. But in this case, because the tag depends on all the past, this OK is clearly referring to the context, which is the sequence of previous messages. So I think it's really convenient, and it comes naturally with the notion of incrementality that is buried in DEC functions. Okay, yeah, I'm going to go quickly over this slide. So we defined a mode called DeXen, which does this session-based encryption using a nonce. And it's really simple, so you initialize it with some nonce, and you can get a tag over the initialization. Let's say you have a first message composed of metadata, something you want to authenticate but not encrypt, and the plaintext. You use the DEC function to produce some key stream, you encrypt it, as done 2 or 3 slides before, and the tag includes everything, including the metadata and the ciphertext. Now, because we already processed the nonce, this nonce is now grayed on my slide. It means we don't need to pay for it. We just pay for this so the metadata and ciphertext. And if I have a second message, then I need to pay the price only for this second message. Okay. All right, so DeXen needs a nonce. It means that you need to have a sequence number, maybe it's a packet number, but if you repeat that value, then you get into trouble. So there are other DEC-based modes that we define. One is called Sensei, and the idea is to replace the sequence number by some synthetic sequence number based only on the plaintext. So you don't need to really maintain this sequence number. And the other one is DEC WBC, wide block cipher. The idea is to achieve authenticated encryption with minimal expansion. So if you have plaintext that already contains some redundancy, you can just base yourself on this redundancy to ensure authenticity. And maybe you want to encrypt something into something else without any expansion. Because of course, in DeXen, DeXen, you have this extra tag that increases the size of your cipher. So you have ciphertext and the tag that you need to transmit, so you have some expansion. With WBC, you can manage, if you have enough redundancy, you can just have your ciphertext whose length is equal to the plaintext, full stop. So that's really a nice feature. Yeah. Then a few minutes about how we can build an efficient DEC function. So recently we developed a new construction called Farfalle. The name Farfalle comes from, yeah, maybe its shape, I don't know. So again, I'm not going to detail everything that's happening inside. So it takes a secret key and some input blocks. But the key thing to look at on this figure is that the permutation F that is being evaluated in this construction, they get all evaluated, they can be evaluated at the same time because they can run in parallel. So you can parallelize your implementation, and maybe you can plug in a vector implementation of this permutation. You can compute 2 permutations at once, 4, 8, depending on the size of your vector SIMD instruction, vector instructions, so they can really speed up things. And the same goes for the output. All these Fs, all these permutations can be computed at the same time. So basically we define two instances of ciphers based on Farfalle. The first one is called Kavate, and Kavate uses a Ketchak permutation reduced to 6 rounds, so that's one F. We claim that it has a security of 128 bits, and we claim that it also includes adversaries who would have access to a quantum computer. So Kavate is fairly fast. The only disadvantage is a big block size of 200 bytes. So we defined another permutation that was done recently called Zudu. That's a 384-bit permutation, so 488 bytes. And we defined Zoof, which is Farfalle, using Zudu with 6 rounds. There again, we claim a security of at least 128 bits. This post-quantum claim was reduced a little bit because the permutation is smaller, and that's just a consequence of this size. So performance figures, so that's Kavate on a Skylake processor. So Skylake processor is a fairly common processor nowadays. It has AVX2 instructions. VX2 are 256-bit SIMD instructions. And using that, we can implement Kavate with a speed that is slightly faster than AES encounter mode on that platform. Bear in mind that on this platform, there is the AES NI instruction. So basically, the AES implementation is a hardware implementation, whereas Kavate uses just the general purpose vector instructions on that machine. Okay, so last thing is about Zoof. So Zoof, as the name suggests, is supposed to be fast. But the key message for Zoof is that because we use a smaller permutation, this permutation, the state can fit in 12 registers of 32 bits. So that can fit in a typical ARM Cortex processor. It can also run fast on small processors. And because of the parallelism, it can also run fast on high-end processors. So concretely on the Cortex M0 processor, that's a fairly small one, it's about 4 to 5 times faster than the AES, and about the same figures the same ratio for Cortex M3. On Skylake, it's slightly slower than the AES encounter mode, but if you have access to the new AVX512 instructions, then it again becomes faster than the AES encounter mode, again using general purpose instructions. So that's all I wanted to say. Just to conclude, in this talk, I tried to explain to you why we think incrementality in symmetric crypto can make protocols simpler. We've seen that with an example, which is Disco. We also think that it can make some modes more natural. The notion of sessions really directly benefits from this incrementality. And then to capture this incrementality, we defined the DEC function interface, and we showed that we could make some efficient schemes based on that, specifically using the Farfalle construction. And that's it. Thank you for your attention.
We've got time for 1 or 2 short questions. So is there any other questions?
Okay, thank you very much for this interesting talk. It was not clear from your description of the Farfalle construction. You can parallelize the encryption and decryption operations, but can you receive messages out of order and validate the MACs that correspond to it? Because that would be a very important use case for things like WireGuard, for instance.
Okay, so if you have out of order messages, so basically the notion of session simply doesn't work. So you cannot really exploit it. The parallelism I was mentioning, it was not about this session mechanism, it's independent. It's just that this construction allows you to implement. So the longer the input, the more parallelism you can exploit, independently of session mechanism if it's out of order or anything.
Yes, the thing is, from the security point of view, we would like to validate MACs as fast as possible to avoid denial of service conditions. So having too large messages is not necessary.
Of course.
Okay.
And that's why in this mode, we have a tag at session startup. So you have a tag that you can immediately check just based on the nonce. So denial of service attacks, I mean, they need to have this tag correct. Otherwise, you can just stop there and you don't need to check the whole message.
Okay. Thank you.
We are out of the time, so thank you for your questions and for your talk.
Thank you.